Assalamu alaikum for those who joined the meeting. The plan is to start in a couple of minutes. So hopefully by 5:04 we'll be starting, inshallah. Okay, I think we'll start in 1 minute. Lot joining. It's good. Okay. So I think Assalamu alaikum all, and thanks for joining the GSO webinar. We're really delighted today to actually have Amin Oraba as the presenter. Just maybe to give you a quick and a very brief introduction to Amin. So Amin is an experienced geophysicist whose career spanning R&D. He worked as contractor operator and he worked in startup environments. Following his master's degree in research by research in geophysics, he began his career as seismic processor as Veritas. And before joining, after that, he joined BP R&D organization in the UK. At BP, he actually supported land assets worldwide and enormous exploration projects, developing a strong focus in high trace density seismic acquisition. Amin has published multiple studies demonstrating the value of high density seismic beyond conventional imaging, demonstrated the value of high density seismic beyond conventional imaging, contributing to a shift in industry thinking from traditional fault-based metrics toward trace density driven approaches. He's known for multiple innovations and developments of new generations of seismic, which is the Nodal seismic technology, and some of you know the Nimble node, which has been a disruptive innovation that led to the creation of the Stride in 2019 and has since transformed the land seismic acquisition globally. Amin currently serves as Chief Geophysicist at Stride, where he drives the development of next-generation seismic solutions, supporting both hydrocarbon exploration and renewable energy application. I think with Amin presenting today, I might basically say that when he gonna present, I want to maybe share something that he already knows with the strides nimble nodes that has been developed here in Oman. So I think that's something that I'm always most fun to actually share. So with that, I'll leave the floor for you, Amin, to basically say maybe I missed lots of things about you in this introduction, and basically the floor is yours. Thank you.
Thank you very much, Mohammed, and salam alaikum, everyone. And really, really happy to be here. And thanks for the invite, well, from you and from the Geological Society of Oman. Yeah, it's always I'm always pleased to present to the Omani community and surrounding, because of the history of the system being initiated in Muscat back in 2013. So the topic I picked for this presentation is how affordable seismic is helping the energy transition and the renewable sectors in general. Whether it's identifying new energy sources or finding rare minerals, subsurface uncertainties has always been a key point in scaling up renewables and their supporting sectors. The understanding of the geology is not just important from a technical point of view, but it's when there is a lot of uncertainty, there's an impact on the costs, because projects become sometimes very conservative. Problem rises, drilling risks increase as well, and that scares off a lot of the investors. And that's a very important point for the renewables, not as much for the oil and gas, who the ball is already rolling for them. And I think seismic, is changing this dynamic. It turns these assumptions about the subsurface into images that people can see. It provides like a direct subsurface structure, images of faults or pathways to targets, or sometimes even fluid, reducing quite substantially the uncertainty before major commitments are made. So the shift we are seeing today, enabled by far more accessible and affordable seismic, and nodal technology is, at least in my opinion, at the core of this. And that's how I'm going to go through this talk, is really to show how nodal systems are making this transformation. Obviously, I have access to Stride data and to Stride projects, so that's going to be my main examples in here. But in general, nodal technologies are indeed making a huge difference for the renewables, as we will see. So the outline of the talk is this 5 points. Dr. Mohammed, so I didn't know what how familiar the audience was with seismic, so I decided just to put a couple of slides to just say what seismic is in a nutshell. I hope experts in the audience are not going to be offended by this, but there's also quite important points that we tend to forget about seismic that I would like to highlight during those couple of slides, and then mention about this, basically the state of the art of seismic that as it is now, and what are the challenges that we're seeing, and then move on how do compact nodes really make the difference through showcasing the impact on real projects across a lot of non-oil and gas industries. As you will see, half of the presentation are actually case studies, and finish with conclusions. Hopefully, I would tend to maybe talk for about 35-40 minutes max. I'll try to time myself to not go beyond that, to leave a good slot for Q&A. Okay, so seismic in a nutshell, in seismic methods in general.
I think,
yes.
Amin, you're not sharing the slides.
Am I not? Oh, sorry. I thought I was. Let me see.
Yes.
Yeah, thank you.
Thank you.
Right, you didn't miss much. I didn't have much pictures before. It was just a title. Yeah, so seismic methods in general, just in geophysical techniques that use artificially or naturally generated seismic waves to map basically the subsurface structures, determine rock properties or geological interface, etc. So in a way, it's very similar to principles are very similar to ultrasound for medical imaging. It's just that the scale is very different. And unfortunately, the wave propagates in a much more complex way through the Earth than they do through human body. But from a simplistic point of view, it's the same. You're putting a source and a receiver on the surface of a body that you're trying to image the inside of. And there are these 3 points that I wanted to highlight for seismic that sometimes people are not familiar, maybe they forget especially for the renewable industries, and where you got where solutions tend to be quite straightforward. It's important to know that first of all, seismic as raw data has very little meaning especially for these industries, because they can't be humanly interpretable. They need to be processed, and that part of processing is important to acknowledge for people who are using seismic as a new tool. For a small project, that could be a few days. Slightly average projects could be a few weeks, months, and big projects in the oil and gas, sometimes they take years to be processed. So that's something to be aware of. You will find out that in most of these oil and gas industry, all the geophysical methods are actually very commonly used, and it's important also to know that different geophysical methods see different properties in the subsurface. Seismic sees contrast in density and velocity, so if there is no contrast in those parameters in what you're trying to achieve, it's very likely that seismic is the right tool for you. And last and not least is that you will hear these two terms, active seismic and passive seismic, and they're both based on recording of vibrations of the Earth, but the one on the left-hand side is the one where you bring your own artificial source, so you have a lot more control and you have a lot more power to image the subsurface. While on the right-hand side, passive is just recording the natural vibration occurring at the surface of the Earth, whether they're due to the most common one, earthquake, for example, microseismic events. You can record those, but also you can record anthropogenic noise around the area, or ocean noise, and you can turn that noise into a useful signal that you could extract some information from the subsurface with. The difference with the right-hand side is that you don't need anything on the source. You don't need a source, so you can just plant receivers and let them record for a few days or a few weeks in the area of interest. So why I think should seismic be useful for renewables? It's because it ticks a lot of boxes. And the first thing is probably the most straightforward is that seismic provides an image that is probably the closest to slicing the Earth with a knife. When you look at the seismic image, or reflection image, you could recognize geological structures, and it's very easy to recognize the geology compared to other geophysical methods where they give you this kind of heat map that you have to guess where things are placed. The other thing is that it has the right resolution for a lot of applications. Resolution of seismic can be few meters in the best cases to hundreds of meters in the worst ones, and that's usually enough to be helpful for a lot of projects for geothermal, CCUS, or even mining. It has a very deep depth of investigation. You could go from tens of meters to thousands of meters. It's not unusual to see events at 7 kilometer, 10 kilometer plus in a seismic section. It's very sensitive to gas content, so it's very important, for example, for CCUS and any industry that injects fluid in the subsurface. It can image fractures. You can extract attributes linked to rock properties. You could do what we call 4D monitoring. So that's a repeated seismic. It gives you like a movie of what's happening in the surface through different points in time. And last one not least is shallow hazard. Is it's seismic not only allow you to identify your target, but actually it allow you to de-risk the path to your target, which is just as important. For example, the first few 100 meters of your well are very important to make sure that they go well. If you drill through a cast or a fault or any hazard in those few shallow hundreds of meters, you could very easily lose your well, and actually the whole project can collapse before that. Renewables actually have very small margin for errors, not like the oil and gas, when they could sometimes kill a well and do another one. Renewables, you kill one well, and that's probably your whole project budget is gone. So what are the blockers for the uptake of seismic in these industries? I just picked 4 here, but I thought are the most common. First of all, the cost, as you would imagine, cost of seismic, especially with conventional traditional methods, is very high. There's an element of complexity, especially with cable systems and area of very difficult access places. Resources as well, finding the right people and the right material to allow you to apply to do your operation safely can be an issue with very bulky and heavy equipment. And the last one and not least, for me, this is probably the most important one, at least for what I've seen working with the renewables in the last few years, is the perceived value. It seems like seismic has been discarded just by default, because you always hear it never delivers the right results. And what I think is happening is that a lot of these industry tried seismic they could afford back in the days, which is not necessarily the seismic they need. And therefore, if you start with not cutting corners, but really being very frugal, too frugal about the number of measurements you need to image or your target or your area you want to survey, you will end up with a wrong image, and therefore you might discard the value of that. What actually I think what's changing now is that you can, with much more accessible seismic equipment, you can actually acquire the seismic you need instead of the seismic you can afford. So obviously we're going to be talking about land seismic, and in lens, in seismic, active seismic, you have the source side and the receiver side. And what we're seeing, or the state of the art in seismic these days, and the last what we have seen in the last few years, that there is an element of simplification, miniaturization, and also distribution. So we see a lot from the source side. We're seeing those really very long, heavy fleets being distributed to single point sources, just working independently. And then in the last few years, we're seeing this quite compact and agile sources being deployed in very difficult terrains. Some of them are quite innovative, like the electromagnetic vibrosize, for example, or the pinpoint from a Canadian company there, it's called Explore, or actually the return of the weight drop, like the one like the PEG 500, which is becoming quite popular for urban acquisitions, etc. So a lot of these sources, they have pros and cons, but at least it gives you the choice to go to a lot of different places, but also to be very agile so that they can follow the receiver system that is getting faster and faster. And what you're seeing on the receiver system is the move from bulky, heavy cables to nodal systems. Those nodal systems are these days becoming very small and very compact. The Stradnot, for example, is actually the size of a geophone, but it actually has a whole recording system inside, and it will literally fit in the palm of your hand. I've got one here in my hand, as you can see. It's just as small as this. So this has a quite significant impact on operation with the simplification of transportation, number of vehicles, less people required, etc. So, and that's how in a way, the Stride as a company, we are disrupting in a way the access to seismic for these renewables is through this technology. So at this point, I'll take 5 minutes to introduce Stride as a company and as a product, as all the data that projects I'll be showing are based on this technology. And so as Mohammed said at the beginning, Stride was created in 2019 as a spin-off of a technology invented inside BP 2013, which I was a part of the development team. And yeah, again, the fun fact that the actually first prototype was developed in Muscat. And since 2019, we put a lot of effort into lowering the access point of seismic or high density seismic, as say, to make it affordable to any industry. And I'll show you the next few slides how has this this has evolved over the past 6 years. So this is the node. It's completely autonomous, it's waterproof, has every GNSS enabled for timing, positioning. The charging is done through induction from the outside and data transfer through an optical link. So you plan this and it will record continuously for a couple of months, non-stop. And it's completely agnostic to the source you're using. Basically, all the nodes these days record continuously. So they are, in a way, you get passive data before you get the active data, but when you get the active, it's extracted from the passive as you bring the source information later on. And actually, the passive data becomes a byproduct of any active seismic survey, which we'll see in a few slides later on. We have put a lot of effort into making deployment very simple as well. So the deployment is stateless. So you plan your survey on your computer and then you put it on the tablet, and the tablet will guide you to the position where you need to deploy the nodes. And a lot of small renewable projects, especially when they start, they do not really have resources to use a contractor. So most of them actually tend to make the first early surveys themselves. Obviously, we offer them the training and the support they need. It's a part of the vision is to really make the utilization of the system the deployment of the system very, very simple. In terms of charging and harvesting is also, we worked a lot on making it very compact, but also very modular. We've got these 3 systems. The one on the two, well, the building block of the charging and harvesting is this drawer we see on the left is called the nest, and actually can charge and harvest 90 nodes simultaneously, and it's about the size of 60 centimeters by 60, like a human chest. And then you've got the mini system with a computer that can run most of universities. We provide these 2 with, and then you got the one in the middle, which is called the Nimble, which is a very modular that can handle a few tens of thousands of nodes, and you can have as many. Well, you can have 1, 2, 3, 6 of these nests all together to help you harvest. The one on the right-hand side is Pro System. It's mainly used by the oil and gas operators using hundreds of thousands of nodes, which is not something we are seeing happening in the renewables yet. All right, so now got some stats just to dive into the how we are seeing renewables projects progressing throughout these years. So this is the kind of global operation for us. We've got more than 1 million nodes now deployed around the world, and we've done 400 seismic projects in the last 6 years, and very diverse. Obviously, you've got a lot of oil and gas, but also geothermal, mining, CCUS, and so on. And if you break down those stats, we can see is that at least this is from last year, so the 64% of our projects were actually outside of the oil and gas industry, and that's mainly led by the mining and the geothermal industry. And if we see try to dig into the trend in the last 6 years, now we can see a clear increase year by year of the use of seismic by this industry. It's clearly led by mining and geothermal for every year, even at the beginning. But also what we're seeing, and that's quite interesting as well, and that's something trend we just started seeing in the last couple of years since 2024, is that there is a shift towards higher value seismic type. So people who could only afford sparse 2D, now they do dense 2D. People who used to do 2D, now they do small 3Ds, etc. So as you can see here, there's a shift from 2D to 3D, quite clear from for the last 2 or 3 years with the project we have been involved in. So how nodal technologies are solving these 4-point challenges I mentioned earlier, so cost, complexity, resources, and perceived value. So in terms of cost, now during those 6 years, we've got enough feedback to come up with average stats from clients, and what we're seeing is that clients are saying that customers saying that there's an average of 40% of cost saving in their projects, plus 75% of equipment cost saving, reduced survey time by a third, and the reduced crew size by pretty much half. And that cost saving, as I said, is allowing this industry to move on to a higher value seismic, and that's what for renewables, you're seeing a progressive move to the next higher value seismic for them, whether it's dense 2D or 3D or how you. And the oil and gas, we're seeing just people moving from denser and denser survey or larger and larger surveys as well. So now I'll move to those case studies I mentioned I have. We go through them just to kind of highlight those solutions or that nodal systems are offering to the renewables to overcome those 4-point challenges. So in terms of reduced complexity, as you can imagine, a node that is that small, light, easy to transport and deploy, and also easy to hide. It makes a huge difference, especially in urban environments. We're seeing an increase of a lot of work in Europe, especially for geothermal and CCUS, being done with our system, and that also has an impact on permitting. The less intrusive your system is, easier it is to get permitting to go through towns and cities. Sometimes it's not required. I think for this project, this is a project for geothermal run in Germany by was testing an electromagnetic vibrosize called the eVibe, and it was what you'd call a completely green acquisition. So that's also another aspect of nodal systems being agnostic to the source. They're actually very agile and very flexible, so you can combine them with very innovative sources to achieve minimal environmental footprint and emission. Results here was very good. The one on the left-hand side is a dynamite line, legacy dynamite line, and on the right-hand side is the continuity of that line. With the eVibe, it wasn't an overlap, unfortunately, but you can still see that the character of the seismic is pretty much the same. This is also quite a substantial, amazing example. So we've seen a lot of geothermal projects being run right from 2020 with our system, but that kind of pace has kept on going until we saw this in 2023, where basically it's the world's densest 3D survey for geothermal application, acquired in Switzerland, 2023. And that's again because it's 100 square kilometer, which is a quite decent size for geothermal, and the whole project was I think it was acquired in about 21 or 22 days. I can't remember. I should have that number here. Anyway, very fast, very agile, and as you can see, the fact that the nodal system are completely independent, autonomous. You could plant them anywhere, so you can have a pretty random geometry across a town where you plant your nodes and shoot whatever you can shoot. Next example. Well, that's the same. Yeah, that's the example. Actually, I had the number here. It was completed in 12 days. So that's how fast you could complete a 3D seismic survey across a town in the middle of Europe. And that was using about more than 20,000 nodes in the for the survey. Straight away, you can see that the upgrade from legacy 2D to modern 3D with nodes straight away shows an improved image of the subsurface. But that's, as I said earlier, that shows the value of seismic. So once an operator or even an investor starts seeing things like these, there's a paradigm shift in how people see seismic and see how they can reduce the uncertainty linked to the subsurface. Obviously, there's no coming back. Once you start to do interpretation on a product like this, you're not going to come back to sparse 2D anymore. So that's that fourth point I was mentioning. That is the perceived value has always been wrong. Well, misled by the wrong seismic acquired in the past. There's an element of simplification with autonomous nodes, just because they, as I said, they record continuously all the time. So there is passive seismic become a free byproduct of continuous recording. So this is a project we did in the UK. Actually, it was a RAF base in up north, and we acquired an active seismic through the area for geothermal applications. But then, as the nodes were recording continuously, with collaboration with Newcastle University, we applied ambient noise tomography using interferometry, and that has given us basically a free byproduct of shear wave velocity that you can see here on the right hand side. And that's something you will always get with autonomous nodes, that they are recording passive. If you bring an active seismic, you can just cut the active from the passive, but the rest can be used for a lot of other passive applications. This is also something we're seeing increased use in the renewable industry, is opportunistic pseudo 3D. That's what I call it. And this is a very good example from a project in Germany. So technically, the project initially was to record every single 2D line individually, which was the initial program. But with autonomous nodes, if you have enough of them, you could just deploy all the receiver lines in one go, and you can program the nodes to start all recording in the future at a future date. And that's what they've done. And then what you do is, once all the lines are live, you can start shooting your lines, 2D lines, one by one, as if it was a normal 2D campaign. So you could shoot very fast, very rapidly. So your window for shooting can be reduced, and that actually reduced the cost quite a lot. But the good thing is that as you're shooting your 2D line, all the other lines are listening. So in addition of having your 2D line, which you see here in the middle, you also get a free 3D, sparse 3D, but still a pseudo 3D that can inform you on, for example, here in the extension of the graben in the direction of the in the 3D direction of your survey. And then and that's something we as I said, we're seeing quite a lot. This opportunistic 3D for 2D. And actually, it's a very good segue, for people who might not be confident in doing a 3D. Having this kind of 2D pseudo 3D approach is sometimes a smooth way to show the value again of a 3D seismic. Here's another one. This was a project we did with the CNRS, the French research organization for hydrogen exploration in the Pyrenees a few years ago. And that was minimalistic, with minimalistic resource. So a lot of students were there to help, but still. So we deployed about 900 nodes over the Pyrenees to record natural microseismicity, and we deployed them in 3C. So as another benefit of the autonomous nodes, at least the stride nodes, because they're accelerometers, if you deploy them horizontally, they will record shear waves. So the idea was to plan two horizontally and one vertically, and you get a three component station, which were deployed over 900 station. And to keep the cost very minimal, what we've done, we did this, what we call a node by post method. So we prepare the nodes in our office in Norway. We send them in a box, they deploy them, and a month later they harvest the nodes and they send them back to us. We extract the data from it and we just deliver the data on the cloud, and they get access to it straight away. So that's a very kind of optimized way of reducing costs, because you don't need to do to send the charging and harvesting and getting the training to how to use the system, etc. That was very successful. The nodes recorded a couple of millions of events, which turned out to be very, very accurate. This is in the middle here. This is the events recorded in the last, I think, 50 years by permanent stations. And here you see the one recorded by the stride nodes. Events like of magnitude -2 at 16 kilometers depth were recorded, which is quite extraordinary. And the approach of the NRS team is that if you have a dense grid of conventional nodal systems, actually that's much better for recording events than having 3 or 4 high sensitivity stations in the region. So there's a compensate for the lack of those very, very, very sensitive parent station that you can't have a lot of them, obviously, and they've actually been extremely expensive. They cost tens of thousands of dollars. The team went a bit beyond just recording events. They turned them into sources, and then we did some tomography, which you can see on the right-hand side, trying to find some indication of synchronization that could have generated the hydrogen that they are measuring at the surface. This was published, so you can look for it. You'll find the papers on the internet. And then, yeah, we've got a lot of examples for mining industry as well. So what we are seeing is at the moment, we're seeing a lot of work being done on extending proven discoveries. So you've got an area where there's some shallow discoveries already known, and then there is an element of seismic to allow you to extend actually these discoveries on slightly deeper regions or different directions. So this is an example from Australia for nickel copper, where basically the north side here, which is the right-hand side, is a known discovery, and then on with the seismic, you could see that the I think it was a basalt intrusion that was well, the element of the nickel copper was linked to it, is going deeper on the left-hand side to this Gossan Hill region. The seismic reveals it, and actually there's also, as I said, with the renewables, you will get a lot of multi-physics, a lot of other geophysical methods that obviously have much lesser resolution, but it can be constrained by structural imaging that seismic brings to the table, as in this example. Here is another one for I think this is also from Australia, and that's also for nickel. Looking for some channel features as well. That's with actually seismic for this one has made the prospect appear much shallower than where it was supposed to. And also there's, as I said, there's the path to the prospect that is important to be known, which is something that most of the other geophysical method will not give you. That might help you to get you that kind of fuzzy heat map, but very rarely will allow you to identify a path to your target. Another example here for silver exploration. Same again, just identifying the extent of your prospect in 3D has huge value for extending your prospect. And this one also is in Botswana for I think that was this one for copper. And again, combination with other geophysical methods usually gives you a quite nice constraint into identifying your target, but also the path to your target and the extent, especially if you have an identified prospect already, the extension of that one. So yeah, it's approaching the end of the presentation now. So in a way, what nodes are providing now is that they can do it all. They can, once you know how to use them properly, you could do your active seismic. You don't have to choose, like you can do your active seismic even 1C or 3C or even 9C if you have a 3C source. You could do the refraction. You can do all those near surface methods like surface wave inversion, even inversion or MASW for people who are familiar with these methods. All these actually they are under the active seismic umbrella, but they can all be done during the same survey. And the passive data as well, it's, as I said, it's a free byproduct of any active seismic. And these days, there's a lot of things you can do with passive data. Obviously, there's microseismic, but also interferometry and use ambient noise tomography, for example, to move to or to get you this additional subsurface information that complement actually your active seismic. These also, not getting into too much details, but in processing, there is also a trend into going into simplification of processing towards what we call basically imaging, with advanced imaging with tools like elastic FWR, for example. And these methods, do require some initial models that if you get them from the active seismic and another one from the passive seismic, like the VS from the passive, will help quite a lot. Actually, gets you to that conversion that will allow you to have quite substantial uplift in your in the speed of your inversion, also the conversion of the inversion. So to conclude, since that seismic can really help diverse renewables industries to de-risk their subsurface activities, we've seen that there is a clear increase of the usage of seismic in renewables and also what are called supporting sectors like mining, for example. We're seeing denser and larger surveys being acquired, and bespoke applications show quite promising future for new seismic acquisition technologies. And we've seen also, especially for the mining industry, that seismic complete and help constrain these solutions for other geophysical methods. We've seen that compact, light, and low-cost nodes present several advantages to facilitate access to high-quality seismic. It lowers the capex, the opex. Simple visualization reduces complexity of the operation. There's a better, as we have seen in a lot of these examples, better data shows actually the true value of seismic to future investors, in a way, and the fact that also these the nodes are agnostic to the source type, offer quite high flexibility and efficiency. Plus, there are the capabilities like 3C and passive, etc. They bring quite a lot of value with basically the same tool. I still think that we are at an early phase of the adoption of seismic as the geophysical tool of choice for renewables, like the oil and gas did few decades ago. However, as better data is acquired, the value of seismic will eventually drive its utilization and increase the success of renewable projects, and therefore increase the investment in this industry. So I think I'm quite positive about it. And the question is no longer if seismic belongs in renewables, but really how fast we can make it standard practice as it is in the oil and gas. So this is the end of my presentation, and happy to take any question.
Thank you, Amin, and really nice to see all those examples showcasing the comeback probably of seismic into in the environmental and the mineral sector, because I think cost was one of the biggest factor, and things are becoming much simpler. So thanks for that. I think we'll start taking questions. So I have a question on the chat box from Ahmed El Harthi, and he says, "What is the maximum frequency of passive seismic you had experienced, and what are the ways to increase the resolution of the passive seismic?"
That's an excellent question. I've never had that question asked before. People always ask what's the lowest frequency you get, and obviously that will define the depth of investigation. But unfortunately, you don't get low frequencies that easily in the region. Actually, you're quite lucky in Oman because you've got the ocean pretty much surrounding your country. So you get a lot of those. The high frequency, yeah, it's a very interesting question because we did a couple of projects. Probably the most it's probably one of that I had hidden here. Probably, let me check. No, removed it. Oh yeah, no, it is. Yeah, it is this one. So this was for archaeological application in here. Example here you see on the right hand side, right bottom right hand side. And this was right in the middle of Padua city center. It's a town in Italy. We worked this with the university, and what you can see here around, I don't know if you can see this bit fade background. It's the it's a Roman amphitheater, and they wanted to image the chamber of basically gladiators underneath, because there's a UNESCO protected church here. It's called the Scroveni Chapel here. Anyway, and for these, we didn't have the low frequency to go deep, but actually we had a lot of high frequencies, and we could capture frequencies up to about 18 hertz. And with that, you could image down to about, well, in this case, down to about 5-8 meters, depending on mostly the lateral resolution was the most important here, but the cavity was expected to be at about 10 meter, well, between 5 and 10 meter. So the issue with high frequencies is how fast they will dissipate. So that's the main issue. But from a technical point of view, interferometry with high frequencies should work just as good as any low frequency as well. But unfortunately, they disappear very quickly in the near surface, and that's a challenge, is to get them above the noise. There have been a lot of stacking here to get to this. I don't know if you can see the ring. See if I do it again, if it will appear. Yeah. So this is a virtual source. There's no source going from the middle. This is just interferometry with the central receiver, creating a virtual shots with a peak frequency of about 18 hertz. That's the highest I've seen, to answer the question more clearly.
Yeah. Do you have any answer in the second part? What ways to increase the resolution from the passive seismic?
Well, the resolution, I don't think you can't increase the vertical resolution. I think vertical resolution will depend on your range of frequencies you get. What's the lowest is the bandwidth. And that's whatever is available. Unfortunately, that's what passive means, is that you work with whatever you've got in the area. So that resolution, vertical resolution, will always be defined by whatever frequencies you've got available to you. The lateral resolution, on the other hand, it's directly linked to the number of points you've got in there, because most of the inversions you have, if you don't do ANT, if you only do like a surface wave inversion, it's a 1D inversion, so you got a 1D profile next to every, well, technically underneath or in between two receivers. So the more of these 1D profiles you get, the higher resolution you're going to get. Obviously, there's still some element of a bit like a Fresnel zone element, where going beyond what the frequency wavelength of the, depending on the geology and the velocities of the near surface, will limit that. But in this case, for example, we had the nodes put at 2 meter, and actually that 2 meter was pretty much the resolution, the lateral resolution we were seeing for this application. So few meter resolution, it's achievable in the right conditions. Lateral, vertical, it will depend on the frequency band you got in the region.
Thank you. I mean, maybe because there's no raised hand, so maybe I might ask a question myself. Based on your experience, given the many projects, how much is the Middle East and maybe Oman is in the picture for using nodal equipments for environmental or mining industry?
We haven't, unfortunately, used the nodes for environmental or mining industry yet. I can see when I'm involved in the HNAT, which is the Conference for Natural Hydrogen, that goes every year. And last year, I've seen a lot of interest in the ophiolites of Oman as a potential area for either natural hydrogen or even what they call it's not induced hydrogen. I forgot the name. It's stimulated hydrogen. So that's something that might become visible in the future. In the region of the Middle East, we've done a lot of projects in the Middle East for geothermal. It's quite interestingly, and mining as well. So, for example, we know that the region of Saudi, there's a lot of opportunities for mining and even geothermal globally. So yeah, I think potentially there's a lot to be done, and I think what's the benefit? Well, not benefit, but the positive thing about applying seismic for both in the Middle East is actually most people are well educated about seismic. It's very different if you when you try to introduce seismic to different part of the world where seismic is a completely foreign method. They're very familiar, for example, with gravity or EM or magnetotelluric for have you. But when you talk about seismic in the Middle East, it's switched on very quickly because oil and gas has been a part of their culture for so long that seismic is just a part of that knowledge, accumulated knowledge.
Thank you. I think we have another question in this chat. How can we use passive surveys in this proposed or within an active ongoing survey? I think I couldn't understand the question. Abdullah, do you want to unmute and you can ask the question? I think I muted you. You can ask the question directly if you wish.
Yes, sir. Thank you, and thank you, Amin, as well. My question is to study ambient noise in certain area. How we can, use a passive seismic survey in studying the ambient noise, or what should be studied during the active seismic survey, during running the active seismic survey, or it's better to study it separately on, or maybe you can give us an information how to deal, how to study ambient noise.
Yeah, so passive data is a free byproduct of nodal systems. So now nodal systems, they don't. So back in the days when you acquired data with cable system, you had to synchronize the cable system with your source. So when the source is shooting, the cables start recording, and then stops recording with a few seconds after the shot is ending, and that's the only data you get. With nodal system, it's not the same. The nodal, you plan the nodes and they start recording non-stop, 24 hours, 7 days a week for about 2 months if you wanted to. So you have continuously passive data throughout the days and nights of your survey, and then when you bring the source in the middle of the day, for example, you just record the time and the position of the source. You give that table to the system, and the system goes and scan the continuous record and extract the active data from the continuous record. But what's remaining is the passive data. So that is perfectly valid for any ambient noise study. And actually, a lot of the projects for the oil and gas, especially in Oman, actually, I know, for example, CGG has done an amazing work extracting ambient noise from continuous record for active seismic to help their elastic FWI with the shear wave velocity model, initial velocity model, and that's exactly what you're asking. Now, whether you do it extracting the data from in between your active activity, or you could also wait until the end of the active survey, if it's not too long, and then you leave the nodes, depending on the size of the survey. But we see this a lot, is that if the survey, if you're using what we call a static spread, and your survey is very quick, it takes 2 or 3 weeks to do, like the one we've seen in I think it's Switzerland. What you could do, you could leave the nodes instead of harvesting them straight away. You just leave them there for another week, and then you get a continuous record of completely non-active for day and night that you could extract and work with. Or you can do it before as well. So you can have the node recording before your active seismic starts. So again, in the nodal systems, because of the nature of the recording, will give you this flexibility of always having a passive data to extract from your active plan survey.
Yeah, thanks, Amin. I think the last question before we close. I think Ahmed Harthi wrote, can vibrators from a very far distance used as a source of a passive source?
Excellent. That's a cheeky question. Yeah. Yes, it's an excellent question, and it has been done. I think the latest project I've heard about this was run by RTS. I believe it was in France. In one of the projects that were initially run for another hydrogen exploration in south west of France. And at the end of the survey, there was a passive recording, and then I think well, at least the idea was there. I'm not sure if it was processed or done, but I remember a chat with Claudio that he intended to bring fiber-size and ask them to shoot around the area randomly without even recording their timing, and that's to bring some diversity in the noise in the region. And I don't see why it wouldn't work. I think it's a great idea. The issue with noise most of the time for passive is when it's not omnidirectional. So if you've got one source of noise in the same point all the time, that completely ruins your passive data. To work well, interferometry requires noise to be coming from all the different directions, very diverse noise from different directions, so that your interferometry would allow you to create proper virtual shots, which are the base of your inversion. So great idea.
Yeah, thank you, Amin. I think we reached the end of our webinar for today. So first of all, thanks from Geological Society of Oman. We thank Amin for the presentation and the rich topic and the many case studies. Really appreciate it. Thanks all for all the attendants, the GSO members and the guests for being with us in the session, asking the questions and interacting. And I think from my side, Mohammed Husni, I thank you all and I hope to see you again in other GSO events. Thank you.
Thank you very much. It was a pleasure. Thank you. Assalamu. Bye.